Okay guys, 2018 free response problem number 3. Let's see what's going on in this one right here. We've been given a graph right here. Always an important idea to note that we are dealing with the graph of G right here. But what's interesting is as soon as we start reading, we see that this is the graph of G, which is the derivative of the function f. So probably right away it's worthwhile to note here that g of x is equal to the derivative of f, or f prime of x. So that's going to be an important relationship to establish right away here in terms of the relationship between g and f. They tell us the function g is piecewise linear for a few parts of this thing right here, namely from -5 to 3, and then all of a sudden it becomes quadratic in between 3 and 6. Okay, so here we go. For part A right there, they tell you the value of f of 1. They want you to come up with the value of f of -5. Almost every time when they give you the value of a function that is not explicitly defined at one x value, and they want you to find it at another x value, that tells us we're going to be using fundamental theorem of Calc part 1. So we're probably going to be using a definite integral right now to come up with, to use 1 and -5 then as your limits of integration. So okay, for part A, I went ahead and set this up. A definite integral going from -5 to 1. And as far as the integrand, I was trying to think of what function we could use here as an integrand that after we antidifferentiate would give us the function f right here for our antiderivative. So in trying to come up with a function that would work that way, we were basically looking at the derivative of the function we wanted to end up with, which was f. So I put an f prime right here. The definite integral from -5 to 1 of f prime of x dx would equal, we would anti-differentiate f prime to get f of 1 and then minus f of 5. And while that may not seem like a whole lot of help, we need to remember that the function we were actually given, g, is the derivative of f. So I made a little note right here that f prime of x was the same thing as g of x, so it might be easier then just to think about this f prime of x as just being a g of x right there. Okay, so in doing that, we were trying to come up here now with the value of this definite integral, and we did that just by looking at the net or signed area underneath this curve right here, starting at -5 and ending over here at 1. So we were looking at a region right here that was a trapezoid that was located below the curve, and then a triangle over here on the right that was above. So to come up with that area for the formula for area of a trapezoid, I put a negative out in front because it was below the x-axis. 1/2, the height of that trapezoid was 3, and the length of its two bases were 4 and 3. Added to that the area of a triangle, 1/2 times a base of 1 times a height of 2. Now that left side there, keep reading now, would be equal to the value of f of 1, which they gave us as 3, minus the value of f of -5, which is exactly what we were trying to find within this problem. I cleaned up that left side a little bit, got a -10.5 plus 1 was equal to 3 minus f of -5. And then moved some things around a little bit. This f of -5 that was negative, I brought it over here to the left, brought everything else over to the right, and answered the question right here that f of -5 would have a value of 12.5. Okay, that was part A. Question B asked us to evaluate a definite integral here from 1 to 6 of g of x. So it was a pretty straightforward question. This was the function they gave us right here, was g, and evaluating this thing from 1 to 6, now we're picking it up at 1, right where we left it before, so on the last problem. So we're looking for the area of that region there, and then this region here going off until 6. Okay, so we wanted to find that total area in red. It's all above the x-axis, so we knew that it was going to be positive. But what made this interesting is that with a piecewise function, we wanted to stop it right here at 3 and count this as region 1, and then kind of these two pieces combined right here we could do as region 2. So this was actually going to take two different integrals in order to figure out what was going on with part B. I mistakenly read this as another fundamental theorem part 1 question, but that is not what we were doing here. So that integral here, let's get working on it. I used the additivity property here and broke it up into an integral from 1 to 3 of g of x plus a second integral from 3 to 6 of g of x, because 3 is the spot where this thing changes its definition. Okay, so moving on from there, the integral from 1 to 3 of g of x, that was just this little square region that we were looking at here, 2 by 2. So that one gave me a value of 4 for that one. And the second part right there, g of x took on this quadratic definition from 3 to 6. So in anti-differentiating that, I raised my exponent by 1 and then divided the previous coefficient 2 by the new exponent of 3 to get this right here. Okay, so the 4 came along for the ride. The 2/3 I put out in front. And then in brackets, I took 6 minus 4 to get 2. Cubed was 8. And then a minus. The 3 minus 4 was a -1. Cubed was a -1 also. That minus negative became a plus there. 2/3 of 9 is 6. And 4 plus 6 got us 10. So 10 was our answer to part B. All right, let's move on to part C. On the interval here from 5 to 6, on what open intervals, if any, is the graph of f both increasing and concave up? And we're supposed to give a reason for our answer there. Okay, increasing and concave up. And when they say give a reason, that usually means that they want it to be something verbal and wordy here, as opposed to justification, which would be a little bit more mathy and numerical. So we had to think about what it was that makes a function increasing and makes a function concave up. And the tricky thing about this is the question is about the function f, but the only function we were given information about was g, which is the derivative of f. So I always like to start a problem like this, maybe backwards from how some people look at it here, and try to think about what I would need to show in order to demonstrate that a function f was increasing. So I wrote a statement that I believe to be universally true here. A function f increases where its derivative, f prime of x, which by the way is equal to g of x, is positive. This is a 100% true statement. A function f increases where f prime of x is positive, always true. I also wanted to know when f was concave up, and concavity is told by the second derivative. So I also wrote then another true statement that f is concave up where its second derivative, f double prime of x. But let's go back to this idea right here, that if g of x was equal to f prime of x, if we differentiated both sides of that equation, we'd get g of prime of x is equal to f double prime of x. So that's a second piece of information that's true as well. So back to where I was, f would be concave up where its second derivative, which is the same thing as g prime, is positive. And that occurs, let's focus just on this concept right here, g prime of x is positive. The derivative of g is positive where the original function, g itself, increases. So these two things that I've underlined here are the important things that I'm looking for. I want to find regions on this graph, intervals, where g of x, the graph we were given, is both positive and increasing. So what do we see right here? In this whole chunk over here, g of x is not positive, it's below the x-axis. But right over here, we have an interval from 0 to 1 where the function is positive, above the x-axis, and increasing. It's not increasing from 1 to 3. It's actually decreasing from 3 to 4. But then again here from 4 to 6, g of x is both positive and increasing. So in answering that question here, both of those things occur on the intervals from 0 to 1 and also the interval from 4 to 6. Now I just noticed right now I have a minor mistake right here. It does say in C in the question, on what open intervals. And I've written them as closed intervals right there. So if I had a pencil or had time to go back and redo all this, I'd probably write those with parentheses rather than with brackets. But the good news is I've never seen an AP grader take off when your parentheses or brackets were off there. They'll give you full credit for either of those. So those really should have been parentheses and not brackets. Oops, my bad. All right, so that's C. And the last question here, D, is similar actually to C. We're going to find the x-coordinate of each point of inflection in the graph of f and give a reason for your answer. Okay, so our definition of a point of inflection is a spot where the second derivative of a function changes sign. So here you go. I again started D really the same way that I started C. A function f has a point of inflection where its second derivative, f double prime of x, but again I just made the note here that f double prime is equal to g prime, changes sign. Well, g prime is going to change sign where its original function, g, is going to change behavior. When g is increasing, its derivative would be positive. When g is decreasing, its derivative would change to negative. So we're looking for spots on this graph right here where g changes behavior. And that one was a little bit interesting here. This was a little more complex. If we think about the behavior of g, we see that it is neither increasing nor decreasing right here. It's staying steady, and then all of a sudden it increases. I would not be surprised if a lot of people thought then that -2 was an answer to this question. But it's not. And the reason why is prior to -2, g prime is 0. Immediately after -2, g prime is positive. Going from 0 to a positive number does not constitute a sign change. Sign changes only go from positive to negative or negative to positive. Similarly, right here at -1, g prime changes from positive to 0, not a sign change. Right here, from 0 to positive, not a sign change. From positive to 0, not a sign change. 0 to negative, not a sign change. But the only interesting spot is right here at 4. G was decreasing, then starts increasing. So the sign of g prime was negative from 3 to 4 and switches to positive from 4 to 6. So the only spot here where f double prime or g prime changes sign, the only one occurs there at x equals 4. And that is a wrap on 2018 problem number 3.